Okay, so today we're going to be talking about an extension of true skewness for unimodal distributions as part of a research done at Oregon State University. I'm Chris, and I did this with my collaborators, Alex Negrón and Clarice Pertel. So before we start, we'd just like to thank our mentor, Professor Yevgeniy Kovchegov, for his guidance, as well as to Professor Holly Swisher for organizing the Oregon State RU. We'd also like to thank the NSF for providing funding for this research. So as a brief outline, we'll just introduce what true skewness is and how it relates to other forms of skewness. We'll present on our theoretical results, and then we'll discuss extensions of our results to other settings. So as background, we care about determining the sign of skewness in order to characterize distributions for which the left tail is spreading short, the right tail is spreading long. And this has application in risk, economics, et cetera. One really commonly used measure of skewness in statistics, for example, is Pearson's moment coefficient of skewness, which is given by the third standardized central moment of a random variable x. We also have this useful heuristic, the mean median mode inequality, which says that for a positively skewed distribution, so one with a longer right tail, that the mode is less than the median, and that's less than the mean. But there are some problems with these measures of skewness. One is that they require the random variable x to have a finite first or third moment, which excludes a large class of heavy tail distributions like the Pareto distribution or the Levy distribution. And moreover, they don't always align. So for example, a distribution with a positive Pearson moment coefficient of skewness might not satisfy the mean median mode inequality and vice versa. So we want to unify these measures of skewness under one universal characterization of skewness.
In order to do this, we define the notion of a p-mean. So for p between 1 and infinity and a continuous random variable x with a finite p minus 1 moment, the p-mean of x is the unique solution nu p of this expectation equation. And we can think of the p-mean as a generalized measure of center of mass. So for example, nu1 would be the median, nu2 would be the mean, and we're dealing with unimodal distributions. So if we have x unimodal, we define nu0 to be the mode. An example of this would be if we take the log normal density function, we plot it with nu0, nu1, nu2, and nu4, we see that these are increasing as a function of nu-p, where nu0 is the dark blue line, nu1 is the teal line, etc.
So now we'll define what true skewness means. So we'll let curly D be the domain on which P, as mentioned above, exists. So when the P minus first moment of X is finite, and we say that X is truly positively skewed if its P means are an increasing function of P on this domain. And the benefit of this is kind of that it first unifies the mean median mode inequality. So clearly if a distribution is truly positively skewed, then the mean median mode inequality holds. And second of all, if a distribution is truly positively skewed, then the Pearson moment coefficient of skewness is also positive. So it's a unifying measure of skewness. And additionally, throughout the talk, we'll only deal with true positive skewness since the theory is the same for true negative skewness.
To show why the notion of true skewness is particularly interesting, we consider the Levy distribution. Visually, at least, it appears the Levy distribution is positively skewed for all values of its shape parameter c. However, we actually don't have a rigorous result that shows the true skewness of the Levy distribution. And this is because the Levy distribution does not have any finite integer moments. And in particular, this implies that the mean, or nu2, and the standard deviation are both infinite. And this means that Pearson's skewness coefficients are undefined. However, using the true skewness theory, we were able to prove the first rigorous result about the positive sign of skewness for the Levy distribution.
Now we'll get into some of the theoretical results relating to what we've done this summer. So as a brief motivation, in general, it's pretty hard to determine the sign of nu-p dp because it's, nu-p is the solution of an integral equation. So it involves analyzing this really long integral differential equation, and we want to develop some tools to determine whether or not d nu p dp is positive or negative without having to deal with this directly.
In Professor Kovchegov's paper, he uses a theorem which involves scaling the left-hand side of a distribution and the right-hand side of a distribution, where they're split along nu p, and then checking to see whether the right-hand side exhibits strict stochastic dominance over the left-hand side. If this is true for all of nu p, of all p, then nu p is increasing at p and x is truly positively skewed. And we're able to establish a proposition which that if f is decreasing on its support, then the stochastic dominance condition holds, and then decreasing densities are truly positively skewed. And one example of using this criteria is the Weibull distribution. So this is for shape parameter k greater than 0, and location parameter 0 and scale parameter 1. Which of course we can assume without loss of generality. We're able to prove necessary and sufficient conditions for the Weibull distribution to be truly mode positively skewed, if and only if the shape parameter is between 0 and 1 over 1 minus log 2, which is roughly 3.26. And additionally, we're able to prove that the Weibull distribution is not truly negatively skewed for any shape parameter greater than 0. So next, we're motivated by this question: is there an easier way to determine true positive skewness? So we have this conjecture: if x and y are continuous random variables that are truly positively skewed, then we conjecture that their convolution is also truly positively skewed. And in general, this is actually false. So counterexample for this is if we have two independent, identically distributed random variables with PDF given by this step function here on the right, with lambda equal to 2/5. So if lambda is less than 1/2, then both x and y are truly positively skewed. And we can see here that f is decreasing. And actually, if lambda is less than or equal to 2/5, then their convolution is not truly positively skewed. So here we have the density function of the convolution for lambda equal to 2/5. And numerically, we are actually able to calculate that nu1 and nu1.1, the difference between they are actually decreasing. So since nu p is not a strictly increasing function, we do not have true positive skewness. So moving on from sums, we're trying to find another class of distributions which are truly positively skewed. And we're intrigued by linear transformations because we know that with positive constants, this preserves true positive skewness. So more generally, we're able to prove a proposition about transformations that says that if we have a continuous random variable x with decreasing PDF, and then we have u of x, a measurable, strictly increasing convex function, then y equal to u of x is truly positively skewed.
So another area of transformations that we're looking at is what happens when we take random variables to their weak limits. So we say that the sequence of random variables converges weakly to x if their cumulative distribution functions fn converge pointwise to the cumulative distribution function f of x, and we use this arrow notation. And intuitively, it seems like because true positive skewness is a function kind of the density or the shape of the density of a distribution, then we can preserve true positive skewness under convolution. In general, this isn't exactly true. For example, if we take xn to be exponentially distributed independent variables, then their partial sums are gamma distributed, which are gamma distributions are truly positively skewed by a result of Kovchegov. So we can apply the central limit theorem to show that gamma distributions upon some scaling and normalization converge weakly to the normal distribution, which is symmetric. So clearly true positive skewness isn't preserved under weak limits. But if we take a slightly more relaxed criteria, so we say that if x is truly non-negatively skewed if d nu p dp is non-negative, which corresponds to nu p being a non-decreasing function of p, as opposed to it being strictly increasing in the case where x is truly positively skewed, then we, using some notation, will, we say nu sub n of p is the p mean of xn. Then if we take a sequence of these xn's that converges weakly to x, and we have some results or some conditions that prevent it from going off to infinity, i.e. that the xn's raised to the power p are uniformly integrable, then if the xn's are truly non-negatively skewed, then x is also truly non-negatively skewed. And note that true non-negative skewness includes true positive skewness as well as symmetric distributions. And if we have a slightly stronger condition, which says that if there exists some c bounded above 0, and such that the derivatives of the nu n of p's are greater than c for all p and d and for all n and n, so uniformly d nu p dp is bounded above 0 for each xn, then the limiting distribution x is truly positively skewed. So one final criteria that we're interested in is, doesn't involve nu p's for most values of p. So if we have x with support on the positive half line, and we assume it has a unimodal density f that's twice continuously differentiable on the positive half line, and it continues at 0, then if we say that f has exactly 2 inflection points, theta 1 and theta 2, such that theta 1 lies to the left of the mode and theta 2 lies to the right of the mode, and we also have these 2 conditions, which are that the logarithmic derivatives are sufficiently bounded. So the first condition says that the density is increasing steeply to the left of the mode and is decreasing shallowly to the right of the mode. And finally, if we check that the median is sufficiently far enough right of the mode, then we can conclude that x is truly positively skewed. And the benefit of using this theorem is that, one, we don't actually need to know nu p for most values of p. We only need to know the mode and the median, which are usually easier to calculate. Secondly, we don't actually need any explicit formula graph, so we can use numerical calculations to verify a lot of the conditions of this theorem, especially maybe with applications to stable distributions. And third, we can relax most of these conditions with some practical costs, but depending on the scenario, we can apply it in a variety of situations. So as an example, we'll look at this density function in red. We can see that the dotted blue lines representing the inflection points lie on either side of the mode, which is the dotted black line. And we have this dashed black line, which is the median, that lies sufficiently far enough right of the mode. And finally, that the left side of the mode is increasing somewhat steeply and the right side of the mode is decreasing shallowly. And this can be calculated. So this fulfills the conditions of that theorem previously, and we can conclude that this density is truly positively skewed.
Up to now, our toolbox for showing a random variable is truly skewed applies only to continuous univariate distributions. And for the rest of the talk, we'll talk about how to interpret the skewness of a multivariate distribution, extending our true skewness ideas to discrete distributions, and finally, how we can quantify skewness. For a continuous univariate distribution, we often show true skewness using a stochastic dominance argument. If the right tail of the distribution stochastically dominates the left tail, then we have a theorem saying that this distribution is truly positively skewed. We're able to prove the theorem stated here, which extends this argument to discrete distributions. It says that if the scaled right tail stochastically dominates the scaled left tail, then this discrete distribution is truly positively skewed.
So we recall that a continuous decreasing distribution is truly positively skewed. So we attempted to develop the same criteria for discrete distributions. We were able to prove the following lemma, which says that the mass function of a binomial random variable x with n greater than 1 and parameter lambda less than or equal to 1 over n plus 1 is a decreasing function on its support. However, by plotting nu p, we actually learned that if x is a discrete distribution with a decreasing function mass function, then it is not truly positively skewed. So here we have nu p for binomial with parameter 2 and 1/3, p between 1.01 and 1.24, and since it is decreasing, it is not truly positively skewed. So ultimately, we've identified that the problem with discrete random variables is that we can model discrete random variables using the Dirac delta function. So if we see here, this green graph is a binomial distribution as a mixture of bump functions. So binomial can be thought of not as a unimodal distribution, but in fact as having n modes.
So in addition to thinking about how to extend true skewness to discrete distributions, we also thought about how to interpret true skewness in multivariate distributions. We define a higher dimensional analog of nu p, which is shown here, but we have to be careful about how we interpret what true skewness means for multivariate distributions. You recall for univariate distributions, true skewness corresponds to the sign of d nu dp. But for a multivariate distribution, d nu dp is a vector, so it doesn't really make sense to talk about its sign. What we do is we define this eta p vector, which is the unit norm derivative of the nu p vector, and we interpret the skewness of a multivariate random variable as the collection of these derivatives indexed by p, and we term this the trajectory eta. And on the next slide, we have some plots and numerical computations that illustrate this idea. It's easiest to interpret the eta trajectory for a bivariate distribution. And on the top left is the density function of a Gaussian mixture distribution, and below is its contour plot. The black arrows on the contour represent some of the eta vectors plotted tip to tail. And this is the trajectory that we were talking about in the previous slide. On the right is another Gaussian mixture distribution that's a little bit more interesting and kind of curves. And you can see that the eta trajectory sort of follows this curvature. And lastly, we'll talk a little bit about how we're approaching a way to quantify true skewness. If you recall the discussion about the Levy distribution, we said that classical measures of skewness are undefined. And the main theme of our approach to skewness so far has been to interpret skewness as the trajectory of d nu dp. But if you look at Pearson skewness measures, they all have this form of a scaling factor times difference of nu p. So it's natural to guess that an appropriate skewness measure might take the form of a scaling factor times d nu dp, which merges our ideas with the classical approach to skewness. And that's the idea of this measure gamma. The integral is the weighted average of d nu dp with respect to a weight function phi, and this is scaled by 1 over the absolute value of nu1 minus nu0. And to obtain the second equality shown here, we simply apply integration by parts to the numerator. So over the years, many skewness measures have been proposed, and it's widely accepted that any skewness measure ought to obey the first of the 3 properties listed here. The first property says that a symmetric distribution should have a skewness measure of 0. And the second property, intuitively speaking, says that if we slide a distribution to the left or right, we shouldn't change its skewness. And if we stretch this distribution everywhere, we also don't change its skewness. And the third property says that if we take a positively skewed distribution, reflect it over the vertical axis, and then measure the skewness of this reflected distribution, we should get the negative of the skewness of the original distribution. It turns out that our skewness measure gamma actually satisfies all 3 of these properties. But more interestingly, given a set of data, we can statistically estimate the skewness of that data using this gamma metric. And to do this, the idea is to replace everywhere you see a nu p with its estimator nu hat. This estimator for nu is a modification of the medioid function, which estimates the center of a set of data. But what about this weight function phi? Intuitively, Pearson skewness measures, we only consider nu p for values of p that are pretty small, p equals 1 or p equals 2. And in general, the higher moments of a distribution tell us less information about the shape of the distribution than the lower moments. So when choosing the weight function phi, the idea is to give more importance to d nu dp when p is relatively small, and to give less importance to d nu dp when p is relatively large. A good candidate for such a function is the sigmoidal function shown here. And this plot shows what a function like this looks like for certain choices of the parameters. So you see that phi takes values close to 1 for p less than about 5, and then phi takes values close to 0 for values of p that are larger than 11 or so. And we think functions like this can be used in the gamma skewness measure. So this concludes our talk. We expect a lot of our future work to refine this measure of skewness, to prove more results about the extensions to multivariate distributions, and in general, the main goal of our research is to establish that a large class of random variables are truly skewed.